Section 3.4, to solve problems involving linear and angular velocity. Our first slide states the definition of angular speed, the amount of rotation per unit of time, where theta is the angular rotation and t is the time. An easier way to state that is, we want to know how big our theta or angle grows over a unit of time. A quick example is to take a look at an analog clock. I have my minute hand at noon, and all I need to do is rotate my second hand 45 degrees. And if I did that in actually 15 seconds, that would give us a measure of 45 degrees in 15 seconds. But we do have some constraints about theta. This slide shows us the constraint on theta, and it must be in radians. Our goal on all of our problems is to always find the angles first, and that would mean to find theta and omega. These statements will help us discover how to find theta and omega in terms of radians over a unit of time. Our first example, a clock rotates 45 degrees in 15 seconds. Our first goal is to get our angle measure from degrees to radians. Recall we do this by multiplying by 45 degrees by pi over 180. When we simplify, that'll give us pi over 4 radians. Now we need to find omega, and omega is going to be theta over t. And when we substitute, that'll give us pi over 4 divided by 15 minutes. And then when we continue to simplify, pi over 4 times 1 over 15, that will give us pi over 60 radians per second. Our next example, a wheel makes a half a revolution in 30 seconds. If we go to the unit circle I have drawn here, we can see if I start 0 degrees to 90 degrees, but recall in radians 90 is pi over 2, 0 to 180 degrees, but at 180 degrees that would give us pi if we converted 180 to radians, and similarly to 270 degrees it would be 3 pi over 2, and 1 complete revolution is 2 pi. For this example, we know that a wheel makes a half a revolution in 30 seconds. Therefore, if we take a look at the unit circle, from 0 degrees to 180 degrees, that would give us a half a revolution, or that would give us a theta that is pi radians. Now that I have my theta, I can just solve for omega. Omega, recall, is theta over t. Here, my theta is going to be pi, and my time is 30 seconds. Then I'm going to have pi over 30 radians per second. Our next example shows a gear that makes 1 revolution in 1 minute. Well, recall that we have 1 revolution, so if we start at 0 degrees and make 360-degree revolution, that is a radian measure of 2 pi. So theta is going to equal 2 pi radians. Now we need to find omega, which is going to equal theta over t, and then we substitute. Theta is 2 pi, and my t is 1 minute. And this will be radians per minute. In my next example, I have a car tire that makes 1,200 revolutions in 2 minutes. From our previous example, I know that 1 revolution is 2 pi radians. This has 1,200 revolutions, so my theta is going to equal 2 pi times 1,200. Therefore, my theta is going to equal 2,400 pi radians. Now I need to find my omega. Omega is going to equal theta over t, which is going to be 2,400 pi over 2 minutes. And when I simplify, that's going to give me an omega that is equal to 1,200 pi radians per minute. Let's continue with another definition, linear speed. This deals with distance traveled per unit of time. Here, speed is defined as distance over time, or velocity equals s over t. And from previous sections, we know what s means, which is arc length, which is going to equal r times theta, where r is the radius of the circle. A good example of linear speed is to take a look at a point that might be on an analog clock. For example, if I put a point on this analog clock, the second hand, and I rotate this, I can see that the distance that this travels, which is the arc length, is going to be a different measure than if that point was furthest out on the radius of that minute second hand, or if it was close. But the factors that are going to help determine linear speed is going to be definitely the radius and the angle measure generated by that movement. The next slide gives us a chart that represents angular speed and linear speed, and there are formulas that represent both of these. As in the previous slides, we have omega, which is theta over time, where theta is going to be in radians, and omega then will be radians per measure of time. We now have the linear speed, which is going to be velocity equals s over t. But recall, s is going to be our arc length, and arc length is determined from our previous sections to be radius times theta, which again is going to be in radians. And recall that our job is to always put our angle measure in terms of radians. But if I would just take this section of the formula, theta over t, that really is omega. So velocity can be represented in several different formats here, and the final one being, which is our radius times omega. I will put this chart on our resource page under our group.